I'm Ben Walker. I work at Intel on the Storage Performance Development Kit. I'm one of the core maintainers, have been for a number of years now. You'll see me a lot on the mailing list, and if you submit patches, you have to get approved by myself and a select other group. Today I'm going to be talking about specifically the NVMe-oF fabrics target that exists in SPDK and some of the design decisions we made there. I'll go into that a little bit more. About how it works today, and that's certainly a lot different than how it worked several years ago. So I guess first things first, don't believe me, I guess that's what it says. So a little bit on the agenda for today. We'll do a little bit of background, not a lot. I'm going to make a lot of assumptions about my audience. Then we'll go through the main part of the talk, which is the design overview of the NVMe-oF fabrics target as it is today. And then we'll end with some benchmarking, which is kind of fun. So I came here 2 years ago and gave a talk on SPDK in the same room, possibly to many people in the same audience, about where we stood then. That was right after we had released the NVMe-oF fabrics target for the first time. The spec had just come out. I think we released it within 24 hours of the spec. Coincidentally, I was losing my voice then, and here we are again, but I'm in much better shape this time, so hopefully I don't cough through it. The design of the NVMe-oF fabrics target that I outlined then doesn't share much in common with the design now. So this talk is a lot about what we learned about how to implement this spec so that you get great performance as you scale up the number of CPU cores, as you scale up the available network bandwidth, as you scale up the number of SSDs, et cetera. So that's the real focus here. Just a little bit of quick background. This is all based on the Storage Performance Development Kit. It's a BSD licensed collection of C libraries, including user space drivers. It's a block stack in user space. And it contains an iSCSI target, an NVMe-oF fabrics target, and a vhost target for serving I/O to VMs. It's entirely open source. It's hosted on GitHub. Jim Harris is one of the other core maintainers and gave a talk about the NVMe driver earlier in the conference. I hope many of you got to go to. Paul Luz yesterday gave a talk on the BDEV layer, which is like our block stack. This builds on all of that to implement an NVMe-oF fabrics target. The original idea of this toolkit was that we saw the shift that everybody at this conference has been talking about for actually many years coming. We saw it coming in 2013-ish, maybe 2012, where the software overhead in the storage stack was going to become significant. And so we started working on this in earnest in 2014. Not the NVMe-oF fabrics target per se, that idea didn't exist. But the idea of a user space, poll mode, entirely asynchronous, lightweight block stack replacement for storage-specific applications. Fortunately for us, things have really panned out to be exactly as we predicted. We were told in 2013 or 2014 that it might be physically possible to create, an SSD with some new interface. It wasn't NVMe. They were thinking about NVMe. But it might be able to create a PCIe attached SSD that, could service reads and writes in 20 microseconds or 10 microseconds. And of course that sends panic across all the software developer community. Because all of the storage stacks then and this is a long time ago now, were designed, we were just sort of coping with Flash at that point, and we were barely around to dealing with that. And all of the decades of software development around storage had been written around assuming that a read takes a millisecond or more. And so everything we knew was out the window. And so we rewrote this thing from the ground up to be fast. And everything we do is fast. And we will make no compromises on the performance. If we cannot implement a feature such that it is performant, we will not implement the feature. That's pretty much our requirement. So that's the only background slide I have. We're going to go into details of NVMe over Fabrics next. So I'm assuming you're at this conference, so you know what NVMe is, and you know roughly how that works. I'm going to assume you mostly know what NVMe over Fabrics is, although I'll go into some details there. And that you all agree that the software overhead of storage stacks is high. All right. So when I came here in 2016 and talked, the requirements we had for writing an NVMe over Fabrics target were essentially, we wanted to leverage the SPDK framework. The block stack then was not entirely fleshed out. And so the first version of the NVMe over Fabrics target just used our NVMe driver directly. We wanted it to be zero copy with an asterisk. When you're using RDMA as the fabric, we want to do zero copy. And by zero copy, I always mean the CPU does no copies, right? So I don't count bouncing data from the NIC into host memory and then to the SSD as a copy. That, I think Stephen Bates gave a talk at this conference about doing peer-to-peer transfers, which is even better. But I'm going to leave that out of it. He actually implemented support in SPDK for that. But it's not been extended to NVMe-oF just yet. But when I say zero copy, I mean we're not copying from one place in host memory to another. It's going to be entirely polled mode for low latency, which we've shown, and a number of other talks throughout this conference have shown is far more efficient and consistent in terms of delivering IOPS. And then the tricky one is we wanted it to scale linearly with the addition of new hardware resources. And that includes CPU cores, networking devices, and storage devices. Okay, so what do we do to achieve linear scaling in software? And so this talk is definitely SPDK focused, but there are some hopefully broader learnings to be taken away here, and these are them. Excuse me. So how do we write software that scales? Scales up. We do so by avoiding locks and atomics, primarily, which is easier said than done. One thing we've decided is okay is that we will make management operations, non-IO operations, arbitrarily time-consuming to avoid blocking the IO path. That doesn't mean they're blocking operations, management. It means they're probably long asynchronous operations that may do lots of cross-thread communication and things like that. But we let the IOs go through as much as we possibly can. We avoid cache contention, CPU cache contention, anywhere we can. We try to keep each core focused on an independent job and a small amount of work, right? So small code is fast code. Keep it in the cache, right? If you have a lot of code that it gets executed on one core, it keeps missing the cache all the time. Keep your code small, do the same thing over and over and over again. And then it needs to be NUMA aware. So one thing you'll see we do all throughout SPDK as a strategy for scaling is that we assign data to threads. We don't take locks, right? We don't have lots of threads access the same data. We assign the data to a thread, and we pass messages. So that gives us our scaling. All right. So now I'm going to outline the design of where we're at now. Not that I promise it'll be this way in 2 more years when I come back. I'll probably have lost my voice then too. This design is very different than 2016. So we'll start with going over the basic primitives in an NVMe or a Fabrics target. So the basic object we call NVMe-oF target, this one. It's this black box. That's the whole thing, all right? So you construct one of those at the beginning of time. Inside of this, it contains some number of subsystems and then one of each type of transport. This is mirroring the way the spec is laid out. So the spec defines something called an NVMe or Fabrics subsystem. I'll talk about what that is shortly. And it has this idea of the pluggable concept of different network transports. The one that is implemented today is RDMA, and I'm going to talk about RDMA quite a bit. And so when I just am talking about transport, I'm usually thinking about RDMA. The Fibre channel transport spec is complete and is implemented in like the Linux kernel. And currently, Broadcom is submitting patches to add that to SPDK for at least their devices. And then, of course, the big talk now is a TCP-based transport, which will be completed imminently. And we will, again, release our code for a TCP transport, the same day as the spec. So most importantly about these objects is that they're what I call global in scope. And so what I mean by global in scope is that all threads in the system are able to read data out of them. They're accessed from lots of different places. So, and that'll be contrasted with other objects which have per thread scope later on. Okay, so subsystems, if we dive just into that subsystem box, the subsystems themselves are global objects. They are composed of a set of controllers and a set of namespaces, again from the NVMe or specification. Notice that namespaces are not in controllers. Namespaces are at the same level as controllers, and that's by spec. I'll explain that a little bit more shortly. That is tough to wrap your head around at first, but makes perfect sense once you realize what these things really are. Subsystems in our implementation have states. This is not in the spec. This is just how we've elected to implement them. And you can only modify the properties of a subsystem while it's not active. So it's basically active paused or inactive just as like the start of time. One other important thing to notice or to note here is that subsystems are entirely virtualized things. The namespace here, each one of these namespaces corresponds to a block device in SPDK, not to a physical NVMe device namespace, right? So it's entirely a virtual thing. This is mapped to an SPDK BDEV, which could map to a libaio device or a Ceph RBD device or, I don't know, anything. The commands that come in and are targeted at namespace are NVMe commands. They're coming in over the fabric. They get translated to our SPDK block layer commands. And then if it happens to be an NVMe device, physical NVMe device behind there, it'll get translated back. So, and this is another deviation from how it worked in 2016, where we were just exposing physical devices over NVMe, over fabrics. Like we just took the NVMe device, the local NVMe device, and it was like pass through the commands, like you just strip off the headers coming out of the network and send it to the NVMe device. That was obviously a lot easier than fully virtualizing it. It's much less flexible. I'm sure Paul went over the benefits of the SPDK BDEV layer. We do logical volume management with snapshots and thin provisioning, and we have inline encryption and someday soon block level compression, and we have RAID 0 and lots of cool stuff in there, right? So that's all behind this mapping of namespaces to BDEVs. We measured the overhead if you do just a plain NVMe-backed BDEV in here, and compared to the old design where we were just mapping physical NVMe drives into the target, and we couldn't really measure the overhead. It was a couple %, and so we elected to just fully virtualize it. Okay, so there's another set of primitives too that sort of mirror the top-level global objects. Again, there was 3 global objects. There was the target, and the set of transports, and the set of subsystems. On each thread, typically, there is an object called a pole group, and inside of a pole group is a set of subsystem pole groups and a set of transport pole groups. And these are per thread mirrors of some of the global data. This is for consistency, it's a strategy to avoid locking. And so the pole groups are not strictly tied to a thread, but that's what we intended, is you create one pole group per thread, and some of the state of the global objects is mirrored into here. And you can read out of that state safely without taking a lock. And if that state needs to change, there's this big global process where it'll send a message to every thread, update the local cache, right, to either hold I/O or do the change on the local cache if it can. If it can't, it'll indicate to the pole group, queue I/O to this subsystem as it comes in, wait for all of them to say, okay, I'm queuing, do the global update, then release them all, right? And this is sort of what I was saying with, we make management operations take arbitrarily long to avoid taking locks on any thread, right? So a management operation almost always requires sending a message to every thread, waiting for them to all respond, doing the operation, sending a message to every thread to tell them to go again. We make it as granular as we possibly can, so that you're not queuing I/O for subsystems or namespaces that you aren't affected by that management operation. And usually if you're doing a management operation on a subsystem, you're doing some pretty serious surgery on it. You're not expecting the I/O to be allowed through while you're reformatting the namespace or something, or deleting namespaces. But you want the thread to not block, because we do everything in sort of a cooperative multitasking fashion, where the threads are just sitting there spinning, pulling the next task off of their queue with one thread per core. And so you can't have that main thread ever block on a lock or something like that, because it blocks operations for other subsystems or for other namespaces. Okay. So we're just continuing to dive down into the objects. So these transport pole groups are interesting. This is part of the way we've gotten our scaling. And this pole group idea didn't exist at all in 2016. What these fundamentally are is a per-thread collection of connections for each transport. So we handle every connection is assigned to a pole group, which means it's assigned to a thread. So each connection individually is mapped to a thread and is only handled by that thread. This collection of connections then is put into some transport-specific grouping such that we can pull that set efficiently for new I/O, right? And so the actual implementations here in RDMA is each connection, which is an RDMA queue pair, is going to share the same completion queue. I'm not really going to talk about Fibre channel. I don't know enough yet. But for TCP, each socket, which is a connection, is going to get put in the same ePOL or KQ group, depending on if it's Linux or FreeBSD. And then we'll pull the set. other than being in the same pole group, these connections are not related to one another. And so I'll talk a little bit about that coming up. But they're not all connections for the same subsystem or for the same controller. Okay. Well, I think I missed a slide here. Oh, no. Okay. So I wanted to just touch on something here because it's important for my next slide. About the implementation of controllers. A controller in NVMe-oF is a network session. So everybody thinks of NVMe devices as having like a physical controller. It's like a chip on the device, right? In NVMe-oF, a controller is a network session. It is a dynamic thing, and it is small, and it is lightweight, and they come and go whenever you establish your first admin queue. And the network session, the state is effectively the registers that would be in the the PCI bar for a real controller. And so, on your network session, you can send commands to like enable it and disable it and reset and all these sort of things. But none of those commands are doing real things to a real device. It's entirely emulated. And the only reason it's modeled that way is so that you can write one driver on the client side and have it work, whether it's RDMA or whatever, or PCIe, et cetera. But controllers are not, in NVMe-oF, are not real things, physical pieces of hardware. It is just a network session. We create them and destroy them as we need them. Similarly, subsystems are not necessarily real things. Subsystems are access control lists, and that's it. So you place a namespace inside of a subsystem. A namespace, again, is a BDEV. That's a real thing. It's a block device, right? You place a set of namespaces inside of a subsystem, and the reason you would place a namespace into a subsystem is to control who can access it. So a subsystem determines which hosts by their identifier. So a subsystem itself has an identifier called an NQN, and it has a list of allowed hosts, which are identified also by NQN. I think it's like NVMe qualified name. Anyway, subsystems, again, are also lightweight things. You can dynamically create and destroy subsystems as you go. There are management commands for those. So that's a big departure from writing a real NVMe driver against a physical device where the controller is a physical thing. You're not creating those. So this takes a little bit to sort of get your mind around. All right, so back to where we were. There it is. So the subsystem poll groups, this is the per thread cache of state from the global subsystem. What this contains is a set of structures called I/O channels. And if you're familiar with SPDK, that's probably, you know what that means, but I'm not going to assume any of that. What you have inside the subsystem is a list of namespaces that you need to be able to submit I/O to. And if we think of those namespaces as NVMe devices, then in order to submit I/O, we have to have an NVMe queue pair to submit I/O to them. In order to not take locks to access that queue pair, we need to have to use the queue pair from only one thread, right? And so what you can think of here is for each namespace, we have a queue pair for this thread because it's in the poll group. Poll group is the per thread structure, right? So these are actually stored in an array that's indexed on the namespace ID. And so when an I/O comes in, you can look up what effectively NVMe queue pair you are going to submit it on by just parsing the command, pulling the namespace ID out, doing an array offset. There you go, submit the command, right? So all of the data structures in this NVMe over Fabric's target are effectively array math. The overhead of the NVMe layer in software is measured in 100 nanoseconds or something. It's nothing, right? Like you could probably just sit and read the assembly. It's so short. It's like a couple ads and that's it.
What's between this point group and the transport point group?
So these are just held inside the same top-level object. You've got a list of the transport poll groups and a list of the subsystem poll groups for this thread object, which is called a generic poll group.
So poll group will exist twice or reference in both groups?
So one side is the network side and one side is the disk side. Okay. So the transport poll groups is all RDMA queue pairs, and the subsystem poll group is all the backing device NVMe queue pairs. And the way you do the lookup between them is you pull the set of network connections to see what are my new incoming commands. You parse the command, which has a namespace ID in it, and it also has from when the connection was established what subsystem it belongs to. So from those two pieces of information, you can grab the subsystem, and then, which we store as just in a pointer from the queue pair object. So you grab the subsystem, and then you do the array math offset on the subsystem poll group to get the right queue pair for your thread for your namespace, and you submit the command. Okay. So this is a little overview of the process of accepting a new connection. Again, this is totally different than the original design. RDMA has a, if you're familiar with that, it has a what's called an event channel. And it's basically a socket, and you can poll it occasionally or block on it however you want, and you get events there. And it's kind of global to the whole system. It's often another thread. And it'll tell you, if you kind of do the same thing as a regular socket where you bind and listen and all these sort of things. And then when a new connection comes in, you get an event over there off to the side. And what you have to do in response to that event is create an RDMA queue pair to represent the connection. In order to create an RDMA queue pair, you have to assign it a RDMA completion queue. And the first attempt at this, we just said every queue pair gets its own completion queue. And I'll explain why that didn't work out when we tried to scale up to enormous numbers of connections. I'll explain that in a bit. So what we do instead is we have, again, there's an RDMA completion queue associated with each poll group, so one per thread. And what we do now is when we get notified that a new connection has come in, we pick a poll group. And I'll talk about how we pick a poll group. But we pass a message over to the thread on which the poll group is being continuously polled. And we say, add this new queue pair. And right then and there, once the message has been passed and it's being processed, we create an RDMA queue pair and we assign it to the completion queue that's associated with that poll group. And then we've actually established the connection. So a little discussion of how do you pick a poll group? So the original idea was, oh man, wouldn't it be great if we could just put all the connections for one subsystem on the same thread, and then we don't have to worry about locking, and it's all great. It's true you would only get one core worth of processing per subsystem, but I mean SPDK can do millions and millions of IOPS on a single core. It's probably not a problem. So the problem with that is, when do you figure out that this connection that you were just notified about, when do you figure out which subsystem it's trying to connect to? And the answer is in the first command that comes across the wire after you've already established the queue pair and chosen the completion queue. So you can't know, right, anything like that. All you know is who it's from. You know the host. So this is a real challenge. With TCP, you don't have this problem because you can move sockets between ePOL groups and add them to ePOL groups at any time, right, later on. But with RDMA, you have to choose the completion queue right up front in order to receive anything, and then it's immutable. You can't change it again. So what we do is we assign them round robin. We have a set of POL groups that correspond to cores, and we just fan them out. Very recently, somebody submitted a patch. I get a lot of patches a day, so I'm not going to try to remember exactly who, but it's much appreciated. That tries to group all connections, incoming connections, by which host is connecting. And at first, you would think maybe that doesn't really help, but actually, when you're doing things like quality of service, you're probably doing that on a per host basis. And so if you can group all the connections from the same host on the same thread, you don't have any coordination problems when you're processing, the QoS rules. So it might play into that a little bit. But those are the only two algorithms we've ever figured out that might work. You could make the round robin sort of NUMA aware based on the incoming NIC, which we're working toward now, but that's like a minor deviation. You basically don't know anything. And so you just, round robin is about as good as you can do. Okay. So I'm just going to go through the process of handling an I/O. Now that we've established a connection, they sent us the first command. It was a connect command, and it told us what subsystem it's for, and we've sort of cached a pointer in our queue pair structure. And now we're ready to do I/O. So a few things to note just as we go through this. There are no locks. It's touching a very small amount of data that's only touched by this thread. So it sits in like the L2 cache, right? Nothing is going to cause it to evict. We're touching really small amounts of data. And the lookups are all basic array math. There's no data structures here. There's nothing complex. It does a lot of add instructions, and that is it. OK, so what happens is on this thread, we start by doing a function called a poll the POL group. And this is like check all the connections on this POL group for incoming commands, right? And we use, again, that efficient mechanism to pull the set. So in this case, we're pulling the single RDMA completion queue for the set of connections. The next thing is we parse the request. The request came in on a particular queue pair. We know what subsystem that's associated with because the first command told us. It has a namespace ID in it if it's a read or a write, so we know the namespace ID. We grab the subsystem POL group that's associated with the subsystem. We give all subsystems unique identifiers, which is actually an index into an array. So inside of the POL group, we have an array of subsystem POL groups, and we jump to the right one using array math. Then inside there, we have a list of I/O channels, which are NVMe queue pairs, the back ones. And those are indexed on namespace ID. So we do 2 array jumps, and we find the right NVMe queue pair. And then we submit it, right? You copy it into the next slot in the NVMe queue pair, ring the doorbell. Now, I talked about this using the direct to NVMe model because I think that's more familiar to people. We're actually submitting this to our BDEV layer, but it works the same way. It's just another layer of abstraction. OK, so what would happen, just as an aside, what would happen if you needed to add a namespace to a subsystem, right? It's all arrays. So adding is not necessarily the end of the world if the array was pre-allocated to be big enough. Removing is a problem. And having to extend the memory of the array is a real problem. So this is when we do this sort of operation where we, in each subsystem POL group, we can mark the subsystem in a thread local way with a state and say like QIO. And so we'll start the operation by sending a message to every POL group, i.e. each thread. And we'll say, for this one subsystem, I need you to QIO. And then they all acknowledge that. and we come back to the main thread. So now we know they've all seen the message, right? And they're going to queue all incoming I/O. Then we change the array, right? The global version of it, the namespace array, and shrink it by 1 or something. And then we send a message to all of them and say, here's what I did to the global version. Please update your local caches to reflect that change, and then release I/O. And so each one of them, as they receive the message, will take their cache and delete the queue pair that they have and change their memory structure, and then drain the queue. So that process doesn't require any locks, right? It probably would be faster time-wise to, if you're measuring the time it takes to create and delete a namespace, to just have everybody take a lock every time they touch the namespace array. And so just take it, change it, release it. But we don't care how long it takes to update a namespace or change the list of namespaces. We care how long it takes to do reads and writes. So we don't want you to take a read and lock every time you do a read and write. So that's the sort of trade we make all the time in SPDK, is reads and writes always get priority. They are not blocked by anything unless they have to be. Of course, if you're doing I/O to a subsystem and we're changing the list of namespaces, we're going to have to queue your I/O because it could become invalid, right? So there's nothing you can do about that. But we don't want to take locks on that thread because it could block other commands that we found for other subsystems that need to go through. Okay. So I guess now the fun part. Some benchmarks here. What this graph is I'm scaling up the number of what I call active connections, and that means these are connections that are actively sending I/O. They happen to be queued up 32 on each connection. So the system here is I have 2 systems connected with RDMA NIC back-to-back, no switch, just direct connected. Let's see, what do we? It's the theoretical maximum number of 4K reads, random reads you could be doing here on this NIC is a little over 1.2 million. We hit it. I mean, we're pretty much right there at the bandwidth limit most of the time here. And all we're doing is we're going from one connection sending, queued up 32 to 2 to 4 to 8 to 16, and just showing it does get a little bit slower, right? But we're trying to show that as you add more connections, it doesn't slow down, right? Because there's more overhead associated with more connections, right? You have to touch more pieces of memory. It's more cache lines. It's more bookkeeping. You're jumping around, like you get I/O from this connection, then you get I/O from this connection. And, as you jump around like that, there's overhead. But we're trying to show here that we're holding it together as much as we can, right? It's not. We're not trying. There isn't a big cost from adding more connections. Okay, and then this is the real beauty. It looks like the most boring graph you'll ever see. Nothing changes, right? But this is what we've been doing the last 2 years. In the first design, this was a slope, downward slope. So what we're doing here is we have one connection that's actually active the entire time. It's at queued up 32, just like before. And what we're doing is we're just connecting more connections and not using them. So if you give every connection its own completion queue, you have to poll the completion queue for every single one of them. And there were actually some really cool effects there. To poll a completion queue is basically touching a new cache line in the CPU. And we saw a major drop-off as soon as the number of cache lines we had to touch to do the polling exceeded the size of the L2 cache. It just fell right off a cliff, right? So this is why we invented the poll group idea, why we have a shared completion queue. Now we're just pulling the same piece of memory over and over and over. It doesn't matter how many connections there are. Excuse me. So it's completely flat. You know, it doesn't matter how many connections you have. It scales perfect. I'm sure this won't be as pretty for ePole because ePole isn't hardware assisted, totally linear like that, but we can hope. Here's a plot of the memory usage versus the number of connections, which looks like you'd expect. For each connection, we allocate requests and responses, and it's linear. We do not allocate we have a shared buffer pool, basically, for the whole target, so the slope here is not very steep. This should easily scale to 10,000 connections, and you wouldn't be very hard-pressed on memory. And then the final one I have is we're doing 4K random reads, again. Excuse me. And then we're giving the target more CPU cores, but having the initiator stay with the same workload. So the initiator has 4 threads submitting I/O on 2 different 25 gig NICs, I think I'm at. I can't remember the speed of the NICs, but we're capping out the NICs by the end. No, it's 100 gig total. It's 4 ports, 2 on each NIC. On the initiator, it's 1 thread per port, sending I/O as fast as it can. The target then has 1 thread at the beginning processing I/O, then it has 2, then it has 3, then it has 4. And so we're round robin assigning the connections as they come in, right? And so it fans them out. And you see it's, as you add more cores, up it goes. All the connections are processed entirely independent of one another. So yeah, and you can see at the end, we're doing, with 4 CPU cores, we're over 4 million IOPS on the target. Yeah.
I guess, can you talk a little bit more of why it's better than linear? Yeah.
I can't get the graph to, it's exactly linear in the real data. Yeah, this one right here, right? This is, I don't know what's going on with Excel, but this is 1.1, and this is 2.2. So 1.1, 2.2, 3.3, 4.4. Yeah, no, people have called that out before, and I cannot get that little thing to render right. Yeah, okay, so perfectly linear scaling as you add CPU cores. And that's it. So I'll take questions. There's no questions? I only had 5 minutes left anyway. Go ahead.
Explain just a little bit more, and I'm not that familiar with this. Can you explain just a little bit more how these fall and why does that create, overhead memory system and so on? Is everything is expected to stay capped at all times and then kind of gets moved one way when I actually goes by the card? Is that what works?
Yeah, we're pulling a few different things. On the RDMA side, we're pulling on the completion queue, which is just checking a bit in host memory that gets pushed out by the card. And then on the NVMe side, on each queue pair for the device, it flips the phase bit inside of the completion to notify you that completion's done. That's how the NVMe spec works. And so we pull on that phase bit. And because, like on Intel platforms, there's DDIO, right? And so when the card flips that phase bit, it puts it right into cache, right? And so if you run this on a system without something like DDIO, it's not great, right? So beware if you port this to some embedded system. There are challenges. You need to prefetch or something. And people have done that. That's why I say that. We know this because people have ported it to embedded systems. It ports very easily. It supports ARM and Power already. but the performance can vary.
What happens as you start, if you have an application of some of the other cores that you're passing data in and out? You have to pay that those cores. This is a matter of how lightweight the infrastructure is. So is there an impact on that?
The message passing is quite light. We're never touching the data. So like all the things we are touching are like little, scatter gather lists or small commands. So the message passing is real cheap. Obviously, if we get stalled out waiting for things to happen in the other application, it's going to be bad. But that's generally how we try to do as much in line as we can. But beyond a certain threshold, yeah, you have to offload it to another core, or you block too many I/O on your. It's like cooperative multitasking, right? You can't take too long. So either you need to break up your operation into multiple steps, and then you can sort of like mux them with all the others, or you've got to put them off on the separate core and pass messages. So we've got message passing infrastructure there that's really lightweight. It's all based on DBDK, which is all proven from like the network space where they do 60 million packets per second or something, passing messages around. It's all based on that. There's an abstraction layer, so you can remove DBDK if you'd like, if you have your own thing. But by default, in all these benchmarks, we're using DBDK to pass messages around. Anything else? Go ahead.
So you described, I guess, 1804. Are you actively looking at something right now to further improve?
In 1807, it was mostly bug fixes. And then in 1810, it'll probably be TCP. So in terms of the scaling and performance, we've got a couple of ideas, but we're getting to the point where it's good enough. And the engineering investment required to do these other things is, we have to ask ourselves, do people really want 1 million connections? It's probably decent enough now for any real scenario. And so what we're focusing on now is really handling like error conditions, like really bad error conditions that are hard to reproduce and these sort of things, and then adding TCP. And Fibre channel work is going on as well. Yep.
So when you mentioned that the transport for the SPDK target is going to be TCP, does that mean there's going to be a usable TCP stack that's coming?
So that's a good question. The first implementation will just be POSIX sockets. But we have an abstraction layer already in SPDK because we have an iSCSI target. And we have an abstraction layer there that allows us to switch between several alternate TCP implementations. The default for iSCSI, of course, is POSIX sockets. That's easy. We'll always do that first. It's very easy to make that work and to test it. The iSCSI target today also supports something called VPP, which is a user space TCP IP stack based on DBDK, written by Cisco and others. There's work ongoing there to actually make that give us a serious performance improvement. Hard engineering work going on there. The SPDK NVMe or Fabrics TCP transport will use that same abstraction. And so for the first release, we're only going to test it with the POSIX sockets, but it will also work with VPP. So, and if there's any other good user space TCP solutions out there that actually give us a performance improvement, we've been looking for years. We want one.
So I know in that SPDK guys have been talking to the company that I work for, but I work for Subsystems.
Oh, yeah.
It's about the user space target. Have you done any performance testing?
No, but SolarFlare has.
I know I have.
No, I think you guys are sending us hardware. So we'll do some work there. Okay, we're out of time.